The lottery ticket hypothesis, finding sparse, trainable neural networks. Abstract. Neural network pruning techniques can reduce the parameter counts of trained networks by over 90%, decreasing storage requirements and improving computational performance of inference without compromising accuracy. However, contemporary experience is that the sparse architectures produced by pruning are difficult to train from the start, which would similarly improve training performance. We find that a standard pruning technique naturally uncovers subnetworks whose initializations made them capable of training effectively. Based on these results, we articulate the lottery ticket hypothesis. Dense, randomly initialized, feed-forward networks contain subnetworks, winning tickets, that, when trained in isolation, reach test accuracy comparable to the original network in a similar number of iterations. The winning tickets we find have won the initialization lottery. Their connections have initial weights that make training particularly effective. We present an algorithm to identify winning tickets and a series of experiments that support the lottery ticket hypothesis and the importance of these fortuitous initializations. We consistently find winning tickets that are less than 10 to 20% of the size of several fully connected and convolutional feed-forward architectures for MNIST and CIFAR10. Above this size, the winning tickets that we find learn faster than the original network and reach higher test accuracy. 1. Introduction. Techniques for eliminating unnecessary weights from neural networks. Pruning. LeCun et al. 1990, Hasibi and Stork 1993, Han et al. 2015, Li et al. 2016 can reduce parameter counts by more than 90% without harming accuracy. Doing so decreases the size, Han et al. 2015, Hinton et al. 2015, or energy consumption, Yang et al. 2017, Molchanov et al. 2016, Luo et al. 2017, of the trained networks, making inference more efficient. However, if a network can be reduced in size, why do we not train this smaller architecture instead in the interest of making training more efficient as well? Contemporary experience is that the architectures uncovered by pruning are harder to train from the start, reaching lower accuracy than the original networks. Consider an example. In Figure 1, we randomly sample and train subnetworks from a fully connected network for MNIST and convolutional networks for CIFAR10. Random sampling models the effect of the unstructured pruning used by LeCun et al. 1990 and Han et al. 2015. Across various levels of sparsity, dashed lines trace the iteration of minimum validation loss and the test accuracy at that iteration. The sparser the network, the slower the learning and the lower the eventual test accuracy. Figure 1, the iteration at which early stopping would occur left, and the test accuracy at that iteration right of the LENET architecture for MNIST and the CONV2, CONV4, and CONV6 architectures for CIFAR10 see Figure 2 when trained starting at various sizes. Dashed lines are randomly sampled sparse networks, average of 10 trials. Solid lines are winning tickets, average of 5 trials. In this paper, we show that there consistently exist smaller subnetworks that train from the start and learn at least as fast as their larger counterparts while reaching similar test accuracy. Solid lines in Figure 1 show networks that we find. Based on these results, we state the lottery ticket hypothesis. The lottery ticket hypothesis. A randomly initialized, dense neural network contains a subnetwork that is initialized such that, when trained in isolation, it can match the test accuracy of the original network after training for at most the same number of iterations. More formally, consider a dense feed-forward neural network f x theta with initial parameters theta equals theta 0 d theta. When optimizing with stochastic gradient descent (SGD) on a training set, f reaches minimum validation loss L at iteration j with test accuracy a. In addition, consider training f x m theta with a mask m element of 0, 1 theta on its parameters such that its initialization is m theta 0. When optimizing with SGD on the same training set with M fixed, F reaches minimum validation loss L at iteration J with test accuracy A. The lottery ticket hypothesis predicts that there is M for which J is less than or equal to J commensurate training time, A is greater than or equal to A commensurate accuracy, and M0 theta fewer parameters. We find that a standard pruning technique automatically uncovers such trainable subnetworks from fully connected and convolutional feed-forward networks. We designate these trainable subnetworks, f x m theta 0, winning tickets, since those that we find have won the initialization lottery with a combination of weights and connections capable of learning. When their parameters are randomly reinitialized f x m theta 0, where theta 0 d theta, our winning tickets no longer match the performance of the original network, offering evidence that these smaller networks do not train effectively unless they are appropriately initialized. Identifying winning tickets. We identify a winning ticket by training a network and pruning its smallest magnitude weights. The remaining, unpruned connections constitute the architecture of the winning ticket. Unique to our work, each unpruned connection's value is then reset to its initialization from original network before it was trained. This forms our central experiment. 1. Randomly initialize a neural network f x theta 0 where theta 0 d theta. 2. Train the network for j iterations, arriving at parameters theta j. 3. Prune p% of the parameters in theta j, creating a mask m. 4. Reset the remaining parameters to their values in theta 0, creating the winning ticket f x m theta 0. As described, this pruning approach is one shot, the network is trained once, p% of weights are pruned, and the surviving weights are reset. However, in this paper, we focus on iterative pruning, which repeatedly trains, prunes, and resets the network over n rounds. Each round prunes p1n% of the weights that survive the previous round. Our results show that iterative pruning finds winning tickets that match the accuracy of the original network at smaller sizes than does one-shot pruning. Results. We identify winning tickets in a fully connected architecture for MNIST and convolutional architectures for CIFAR10 across several optimization strategies SGD, momentum, and ADAM with techniques like dropout, weight decay, batch norm, and residual connections. We use an unstructured pruning technique, so these winning tickets are sparse. In deeper networks, our pruning-based strategy for finding winning tickets is sensitive to the learning rate. It requires warm-up to find winning tickets at higher learning rates. The winning tickets we find are 10 to 20% or less of the size of the original network, smaller size. Down to that size, they meet or exceed the original network's test accuracy, commensurate accuracy in at most the same number of iterations, commensurate training time. When randomly reinitialized, winning tickets perform far worse, meaning structure alone cannot explain a winning ticket's success. Figure 2, architectures tested in this paper. Convolutions are 3 by 3. Lennet is from LeCun et al., 1998. CONV2, 4/6 of variants of VGG, Simonian and Zisserman, 2014. RESNET 18 is from He et al., 2016. VGG 19 for CIFAR10 is adapted from Liu et al., 2019. Initializations are Gaussian Glorit and Bengio, 2010. Brackets denote residual connections around layers. The lottery ticket conjecture. Returning to our motivating question, we extend our hypothesis into an untested conjecture that SGD seeks out and trains a subset of well-initialized weights. Dense, randomly initialized networks are easier to train than the sparse networks that result from pruning because there are more possible subnetworks from which training might recover a winning ticket. Contributions. We demonstrate that pruning uncovers trainable subnetworks that reach test accuracy comparable to the original networks from which they derived in a comparable number of iterations. We show that pruning finds winning tickets that learn faster than the original network while reaching higher test accuracy and generalizing better. We propose the lottery ticket hypothesis as a new perspective on the composition of neural networks to explain these findings. Implications. In this paper, we empirically study the lottery ticket hypothesis. Now that we have demonstrated the existence of winning tickets, we hope to exploit this knowledge to improve training performance. Since winning tickets can be trained from the start in isolation, a hope is that we can design training schemes that search for winning tickets and prune as early as possible. Design better networks. Winning tickets reveal combinations of sparse architectures and initializations that are particularly adept at learning. We can take inspiration from winning tickets to design new architectures and initialization schemes with the same properties that are conducive to learning. We may even be able to transfer winning tickets discovered for one task to many others. Improve our theoretical understanding of neural networks. We can study why randomly initialized feed-forward networks seem to contain winning tickets and potential implications for theoretical study of optimization Du et al., 2019, and generalization Zhou et al., 2018, Aurora et al., 2018. 2 winning tickets in fully connected networks. In this section, we assess the lottery ticket hypothesis as applied to fully connected networks trained on MNIST. We use the LENET 300-100 architecture LeCun et al., 1998 as described in Figure 2. We follow the outline from Section 1. After randomly initializing and training a network, we prune the network and reset the remaining connections to their original initializations. We use a simple layer-wise pruning heuristic, remove a percentage of the weights with the lowest magnitudes within each layer as in Han et al., 2015. Connections to outputs are pruned at half of the rate of the rest of the network. We explore other hyperparameters in Appendix G, including learning rates, optimization strategies SGD, momentum, initialization schemes, and network sizes. Figure 3, test accuracy on Lennet iterative pruning as training proceeds. Each curve is the average of 5 trials. Labels are PM, the fraction of weights remaining in the network after pruning. Error bars are the minimum and maximum of any trial. Notation. PM equals M0. Theta is the sparsity of mask M, e.g., PM equals 25% when 75% of weights are pruned. Iterative pruning. The winning tickets we find learn faster than the original network. Figure 3 plots the average test accuracy when training winning tickets iteratively pruned to various extents. Error bars are the minimum and maximum of 5 runs. For the first pruning rounds, networks learn faster and reach higher test accuracy the more they are pruned, left graph in Figure 3. A winning ticket comprising 51.3% of the weights from the original network, i.e., PM equals 51.3%, reaches higher test accuracy faster than the original network but slower than when PM equals 21.1%. When PM less than 21.1%, learning slows, middle graph. When PM equals 3.6%, a winning ticket regresses to the performance of the original network. A similar pattern repeats throughout this paper. Figure 4a summarizes this behavior for all pruning levels when iteratively pruning by 20% per iteration, blue. On the left is the iteration at which each network reaches minimum validation loss, i.e., when the early stopping criterion would halt training, in relation to the percent of weights remaining after pruning. In the middle is test accuracy at that iteration. We use the iteration at which the early stopping criterion is met as a proxy for how quickly the network learns. The winning tickets learn faster as PM decreases from 100% to 21%, at which point early stopping occurs 38% earlier than for the original network. Further pruning causes learning to slow, returning to the early stopping performance of the original network when PM equals 3.6%. Test accuracy increases with pruning, improving by more than 0.3 percentage points when PM equals 13.5%. After this point, accuracy decreases, returning to the level of the original network when PM equals 3.6%. At early stopping, training accuracy, Figure 4a, right, increases with pruning in a similar pattern to test accuracy, seemingly implying that winning tickets optimize more effectively but do not generalize better. However, at iteration 50,000, Figure 4b, iteratively pruned winning tickets still see a test accuracy improvement of up to 0.35 percentage points in spite of the fact that training accuracy reaches 100% for nearly all networks. Appendix D, Figure 12. This means that the gap between training accuracy and test accuracy is smaller for winning tickets, pointing to improved generalization. Random initialization. To measure the importance of a winning ticket's initialization, we retain the structure of a winning ticket, i.e., the mask M, but randomly sample a new initialization theta, 0d theta. We randomly reinitialize each winning ticket 3 times, making 15 total per point in Figure 4. We find that initialization is crucial for the efficacy of a winning ticket. The right graph in Figure 3 shows this experiment for iterative pruning. In addition to the original network and winning tickets at PM equals 51% and 21% are the random initialization experiments. Where the winning tickets learn faster as they are pruned, they learn progressively slower when randomly reinitialized. The broader results of this experiment are orange line in Figure 4a. Unlike winning tickets, the reinitialized networks learn increasingly slower than the original network and lose test accuracy after little pruning. The average reinitialized iterative winning tickets test accuracy drops off from the original accuracy when PM equals 21.1%, compared to 2.9% for the winning ticket. When PM equals 21%, the winning ticket reaches minimum validation loss 2.51x faster than when reinitialized and is half a percentage point more accurate. All networks reach 100% training accuracy for PM is greater than or equal to 5%. Figure 4, early stopping iteration and accuracy of RESNET under one shot and iterative pruning. Average of 5 trials, error bars for the minimum and maximum values. At iteration 50,000, training accuracy approximately equals 100% for PM is greater than or equal to 2% for iterative winning tickets. See Appendix D, Figure 12. Figure 4b therefore shows that the winning tickets generalize substantially better than when randomly reinitialized. This experiment supports the lottery ticket hypothesis emphasis on initialization. The original initialization withstands and benefits from pruning, while the random initialization's performance immediately suffers and diminishes steadily. One-shot pruning. Although iterative pruning extracts smaller winning tickets, repeated training means they are costly to find. One-shot pruning makes it possible to identify winning tickets without this repeated training. Figure 4c shows the results of one-shot pruning, green, and randomly reinitializing, red. One-shot pruning does indeed find winning tickets. When 67.5% is greater than or equal to PM is greater than or equal to 17.6%, the average winning tickets reach minimum validation accuracy earlier than the original network. When 95.0% is greater than or equal to PM is greater than or equal to 5.17%, test accuracy is higher than the original network. However, iteratively pruned winning tickets learn faster and reach higher test accuracy at smaller network sizes. The green and red lines in Figure 4c are reproduced on the logarithmic axes of Figure 4a, making this performance gap clear. Since our goal is to identify the smallest possible winning tickets, we focus on iterative pruning throughout the rest of the paper. 3 winning tickets in convolutional networks. Here, we apply the lottery ticket hypothesis to convolutional networks on CIFAR10, increasing both the complexity of the learning problem and the size of the networks. We consider the CONV2, CONV4, and CONV6 architectures in Figure 2, which are scaled-down variants of the VGG Simonian and Zisserman 2014 family. The networks have 2, 4, or 6 convolutional layers followed by 2 fully connected layers. Max pooling occurs after every 2 convolutional layers. The networks cover a range from near fully connected to traditional convolutional networks, with less than 1% of parameters in convolutional layers in CONV2 to nearly 2/3 in CONV6. Finding winning tickets. The solid lines in Figure 5 top show the iterative lottery ticket experiment on CONV2 blue, CONV4 orange, and CONV6 green at the per-layer pruning rates from Figure 2. The pattern from RESNET in Section 2 repeats. As the network is pruned, it learns faster and test accuracy rises as compared to the original network. In this case, the results are more pronounced. Figure 5, early stopping iteration and test and training accuracy of the CONV2, 4/6 architectures when iteratively pruned and when randomly reinitialized. Each solid line is the average of 5 trials, each dashed line is the average of 15 initializations, 3 per trial. The bottom right graph plots test accuracy of winning tickets at iterations corresponding to the last iteration of training for the original network: 20,000 for CONV2, 25,000 for CONV4, and 30,000 for CONV6. At this iteration, training accuracy approximately equals 100% for PM is greater than or equal to 2% for winning tickets. See Appendix D. Winning tickets reach minimum validation loss at best 3.5x faster for CONV2, PM equals 8.8%, 3.5x for CONV4, PM equals 9.2%, and 2.5x for CONV6, PM equals 15.1%. Test accuracy improves at best 3.4 percentage points for CONV2, PM equals 4.6%, 3.5 for CONV4, PM equals 11.1%, and 3.3 for CONV6, PM equals 26.4%. All 3 networks remain above their original average test accuracy when PM greater than 2%. As in Section 2, training accuracy at the early stopping iteration rises with test accuracy. However, at iteration 20,000 for CONV2, 25,000 for CONV4, and 30,000 for CONV6, the iterations corresponding to the final training iteration for the original network, training accuracy reaches 100% for all networks when PM is greater than or equal to 2%. Appendix D, Figure 13, and winning tickets still maintain higher test accuracy. Figure 5 bottom right. This means that the gap between test and training accuracy is smaller for winning tickets, indicating they generalize better. Random initialization. We repeat the random initialization experiment from Section 2, which appears as the dashed lines in Figure 5. These networks again take increasingly longer to learn upon continued pruning. Just as with RESNET on MNIST, Section 2, test accuracy drops off more quickly for the random initialization experiments. However, unlike RESNET, test accuracy at early stopping time initially remains steady and even improves for CONV2 and CONV4, indicating that, at moderate levels of pruning, the structure of the winning tickets alone may lead to better accuracy. Dropout. Srivastava al. 2014, Hinton al. 2012 improves accuracy by randomly disabling a fraction of the units, i.e., randomly sampling a subnetwork, on each training iteration. Baldi and Sadovsky 2013 characterize dropout as simultaneously training the ensemble of all subnetworks. Since the lottery ticket hypothesis suggests that one of these subnetworks comprises a winning ticket, it is natural to ask whether dropout and our strategy for finding winning tickets interact. Figure 6 shows the results of training CONV2, CONV4, and CONV6 with a dropout rate of 0.5. Dashed lines are the network performance without dropout, the solid lines in Figure 5. We continue to find winning tickets when training with dropout. Dropout increases initial test accuracy 2.1, 3.0, and 2.4 percentage points on average for CONV2, CONV4, and CONV6, respectively, and iterative pruning increases it further up to an additional 2.3, 4.6, and 4.7 percentage points, respectively, on average. Learning becomes faster with iterative pruning as before, but less dramatically in the case of CONV2. Figure 6, early stopping iteration and test accuracy at early stopping of CONV2, 4/6 when iteratively pruned and trained with dropout. The dashed lines are the same networks trained without dropout, the solid lines in Figure 5. Learning rates are 0.0003 for CONV2 and 0.0002 for CONV4 and CONV6. Figure 7, test accuracy at 30K, 60K, and 112K iterations of VGG19 when iteratively pruned. These improvements suggest that our iterative pruning strategy interacts with dropout in a complementary way. Srivastava al. 2014 observed that dropout induces sparse activations in the final network. It is possible that dropout induced sparsity primes a network to be pruned. If so, dropout techniques that target weights 1 al. 2013 or learn per weight dropout probabilities Molchanov al. 2017, Luizos al. 2018 could make winning tickets even easier to find. 4 VGG and RESNET for CIFAR10. Here, we study the lottery ticket hypothesis on networks evocative of the architectures and techniques used in practice. Specifically, we consider VGG-style deep convolutional networks VGG19 on CIFAR10, Simonian and Zisserman 2014, and residual networks RESNET18 on CIFAR10, He al. 2016. These networks are trained with batch norm, weight decay, decreasing learning rate schedules, and augmented training data. We continue to find winning tickets for all of these architectures. However, our method for finding them, iterative pruning, is sensitive to the particular learning rate used. In these experiments, rather than measure early stopping time, which, for these larger networks, is entangled with learning rate schedules, we plot accuracy at several moments during training to illustrate the relative rates at which accuracy improves. Global pruning. On LENIT and CONV2, 4/6, we prune each layer separately at the same rate. For RESNET18 and VGG19, we modify this strategy slightly. We prune these deeper networks globally, removing the lowest magnitude weights collectively across all convolutional layers. In Appendix I.1, we find that global pruning identifies smaller winning tickets for RESNET18 and VGG19. Our conjectured explanation for this behavior is as follows. For these deeper networks, some layers have far more parameters than others. For example, the first two convolutional layers of VGG19 have 1728 and 36,864 parameters, while the last has 2.35 million. When all layers are pruned at the same rate, these smaller layers become bottlenecks, preventing us from identifying the smallest possible winning tickets. Global pruning makes it possible to avoid this pitfall. Figure 8, test accuracy at 10K, 20K, and 30K iterations of RESNET18 when iteratively pruned. VGG19. We study the variant VGG19 adapted for CIFAR10 by Liu al. 2019. We use the same training regime and hyperparameters 160 epochs 112,480 iterations with SGD with momentum 0.9 and decreasing the learning rate by a factor of 10 at 80 and 120 epochs. This network has 20 million parameters. Figure 7 shows the results of iterative pruning and random initialization on VGG19 at two initial learning rates, 0.1 used in Liu al. 2019 and 0.01. At the higher learning rate, iterative pruning does not find winning tickets, and performance is no better than when the pruned networks are randomly reinitialized. However, at the lower learning rate, the usual pattern reemerges, with subnetworks that remain within 1 percentage point of the original accuracy while PM is greater than or equal to 3.5%. They are not winning tickets, since they do not match the original accuracy. When randomly reinitialized, the subnetworks lose accuracy as they are pruned in the same manner as other experiments throughout this paper. Although these subnetworks learn faster than the unpruned network early in training, Figure 7 left, this accuracy advantage erodes later in training due to the lower initial learning rate. However, these subnetworks still learn faster than when reinitialized. To bridge the gap between the lottery ticket behavior of the lower learning rate and the accuracy advantage of the higher learning rate, we explore the effect of linear learning rate warm-up from 0 to the initial learning rate over k iterations. Training VGG19 with warm-up k equals 10,000, green line, at learning rate 0.1 improves the test accuracy of the unpruned network by about 1 percentage point. Warm-up makes it possible to find winning tickets, exceeding this initial accuracy when PM is greater than or equal to 1.5%. RESNET18. RESNET18 He al. 2016 is a 20-layer convolutional network with residual connections designed for CIFAR10. It has 271,000 parameters. We train the network for 30,000 iterations with SGD with momentum 0.9, decreasing the learning rate by a factor of 10 at 20,000 and 25,000 iterations. Figure 8 shows the results of iterative pruning and random initialization at learning rates 0.1 used in He al. 2016 and 0.01. These results largely mirror those of VGG. Iterative pruning finds winning tickets at the lower learning rate but not the higher learning rate. The accuracy of the best winning tickets at the lower learning rate 89.5% when 41.7% is greater than or equal to PM is greater than or equal to 21.9% falls short of the original network's accuracy at the higher learning rate 90.5%. At lower learning rate, the winning ticket again initially learns faster, left plots of Figure 8, but falls behind the unpruned network at the higher learning rate later in training, right plot. Winning tickets trained with warm-up close the accuracy gap with the unpruned network at the higher learning rate, reaching 90.5% test accuracy with learning rate 0.03, warm-up, K equals 20,000, at PM equals 27.1%. For these hyperparameters, we still find winning tickets when PM is greater than or equal to 11.8%. Even with warm-up, however, we could not find hyperparameters for which we could identify winning tickets at the original learning rate, 0.1. 5. Discussion. Existing work on neural network pruning, e.g., Han et al. 2015, demonstrates that the function learned by a neural network can often be represented with fewer parameters. Pruning typically proceeds by training the original network, removing connections, and further fine-tuning. In effect, the initial training initializes the weights of the pruned network so that it can learn in isolation during fine-tuning. We seek to determine if similarly sparse networks can learn from the start. We find that the architectures studied in this paper reliably contain such trainable subnetworks, and the lottery ticket hypothesis proposes that this property applies in general. Our empirical study of the existence and nature of winning tickets invites a number of follow-up questions. The importance of winning ticket initialization. When randomly reinitialized, a winning ticket learns more slowly and achieves lower test accuracy, suggesting that initialization is important to its success. One possible explanation for this behavior is these initial weights are close to their final values after training, that in the most extreme case, they are already trained. However, experiments in Appendix F show the opposite, that the winning ticket weights move further than other weights. This suggests that the benefit of the initialization is connected to the optimization algorithm, dataset, and model. For example, the winning ticket initialization might land in a region of the loss landscape that is particularly amenable to optimization by the chosen optimization algorithm. Liu et al. 2019 find that pruned networks are indeed trainable when randomly reinitialized, seemingly contradicting conventional wisdom and our random initialization experiments. For example, on VGG19, for which we share the same setup, they find that networks pruned by up to 80% and randomly reinitialized match the accuracy of the original network. Our experiments in Figure 7 confirm these findings at this level of sparsity, below which Liu et al. Do not present data. However, after further pruning, initialization matters. We find winning tickets when VGG19 is pruned by up to 98.5%. When reinitialized, these tickets reach much lower accuracy. We hypothesize that, up to a certain level of sparsity, highly overparameterized networks can be pruned, reinitialized, and retrained successfully. However, beyond this point, extremely pruned, less severely overparameterized networks only maintain accuracy with fortuitous initialization. The importance of winning ticket structure. The initialization that gives rise to a winning ticket is arranged in a particular sparse architecture. Since we uncover winning tickets through heavy use of training data, we hypothesize that the structure of our winning tickets encodes an inductive bias customized to the learning task at hand. Cohen and Shashua 2016 show that the inductive bias embedded in the structure of a deep network determines the kinds of data that it can separate more parameter efficiently than can a shallow network. Although Cohen and Shashua 2016 focus on the pooling geometry of convolutional networks, a similar effect may be at play with the structure of winning tickets, allowing them to learn even when heavily pruned. The improved generalization of winning tickets. We reliably find winning tickets that generalize better, exceeding the test accuracy of the original network while matching its training accuracy. Test accuracy increases and then decreases as we prune, forming an Occam's-Hill, Rasmussen and Garamani 2001, where the original, overparameterized model has too much complexity, perhaps overfitting, and the extremely pruned model has too little. The conventional view of the relationship between compression and generalization is that compact hypotheses can better generalize. RESNET, 1986. Recent theoretical work shows a similar link for neural networks, proving tighter generalization bounds for networks that can be compressed further. Zhou et al. 2018 for pruning, quantization and Aurora et al. 2018 for noise robustness. The lottery ticket hypothesis offers a complementary perspective on this relationship, that larger networks might explicitly contain simpler representations. Implications for neural network optimization. Winning tickets can reach accuracy equivalent to that of the original, unpruned network, but with significantly fewer parameters. This observation connects to recent work on the role of overparameterization in neural network training. For example, Du et al. 2019 prove that sufficiently overparameterized two-layer ReLU networks with fixed-size second layers trained with SGD converge to global optima. A key question, then, is whether the presence of a winning ticket is necessary or sufficient for SGD to optimize a neural network to a particular test accuracy. We conjecture, but do not empirically show, that SGD seeks out and trains a well-initialized subnetwork. By this logic, overparameterized networks are easier to train because they have more combinations of subnetworks that are potential winning tickets. 6 Limitations and future work. We only consider vision-centric classification tasks on smaller datasets MNIST, CIFAR10. We do not investigate larger datasets, namely ImageNet. Ruzakovsky al. 2015. Iterative pruning is computationally intensive, requiring training a network 15 or more times consecutively for multiple trials. In future work, we intend to explore more efficient methods for finding winning tickets that will make it possible to study the lottery ticket hypothesis in more resource-intensive settings. Sparse pruning is our only method for finding winning tickets. Although we reduce parameter counts, the resulting architectures are not optimized for modern libraries or hardware. In future work, we intend to study other pruning methods from the extensive contemporary literature, such as structured pruning, which would produce networks optimized for contemporary hardware, and non-magnitude pruning methods, which could produce smaller winning tickets or find them earlier. The winning tickets we find have initializations that allow them to match the performance of the unpruned networks at sizes too small for randomly initialized networks to do the same. In future work, we intend to study the properties of these initializations that, in concert with the inductive biases of the pruned network architectures, make these networks particularly adept at learning. On deeper networks RESNET 18 and VGG 19, iterative pruning is unable to find winning tickets unless we train the networks with learning rate warm-up. In future work, we plan to explore why warm-up is necessary and whether other improvements to our scheme for identifying winning tickets could obviate the need for these hyperparameter modifications. 7. Related work. In practice, neural networks tend to be dramatically overparameterized. Distillation Barr and Caruana, 2014, Hinton al. 2015, and pruning LeCun al. 1990, Han al. 2015 rely on the fact that parameters can be reduced while preserving accuracy. Even with sufficient capacity to memorize training data, networks naturally learn simpler functions. Zhang al. 2016, Naishabur al. 2014, Arpit al. 2017. Contemporary experience Bengio al. 2006, Hinton al. 2015, Zhang al. 2016, and Figure 1 suggest that overparameterized networks are easier to train. We show that dense networks contain sparse subnetworks capable of learning on their own starting from their original initializations. Several other research directions aim to train small or sparse networks. Prior to training, SqueezeNet Iandola al. 2016 and MobileNets Howard al. 2017 are specifically engineered image recognition networks that are an order of magnitude smaller than standard architectures. Denil al. 2013 represent weight matrices as products of lower rank factors. Li al. 2018 restrict optimization to a small, randomly sampled subspace of the parameter space, meaning all parameters can still be updated. They successfully train networks under this restriction. We show that one need not even update all parameters to optimize a network, and we find winning tickets through a principled search process involving pruning. Our contribution to this class of approaches is to demonstrate that sparse, trainable networks exist within larger networks. After training, distillation Barr and Caruana, 2014, Hinton al. 2015 trains small networks to mimic the behavior of large networks. Small networks are easier to train in this paradigm. Recent pruning work compresses large models to run with limited resources, e.g., on mobile devices. Although pruning is central to our experiments, we study why training needs the overparameterized networks that make pruning possible. LeCun al. 1990 and Hasibi and Stork 1993 first explored pruning based on second derivatives. More recently, Han al. 2015 showed per-weight magnitude-based pruning substantially reduces the size of image recognition networks. Guo al. 2016 restore pruned connections as they become relevant again. Han al. 2017 and Jin al. 2016 restore pruned connections to increase network capacity after small weights have been pruned and surviving weights fine-tuned. Other proposed pruning heuristics include pruning based on activations Hu al. 2016, redundancy Marriott and SRA, 2016, Srinivas and Babu, 2015a, per layer second derivatives Dong al. 2017, and energy, computation efficiency Yang al. 2017 e.g., pruning convolutional filters Li al. 2016, Molchanov al. 2016, Luo al. 2017, or channels He al. 2017. Cohen al. 2016 observe that convolutional filters are sensitive to initialization, the filter lottery. Throughout training, they randomly reinitialize unimportant filters. During training, Belek al. 2018 train with sparse networks and replace weights that reach zero with new random connections. Srinivas al. 2017 and Louis Oz al. 2018 learn gating variables that minimize the number of non-zero parameters. Narang al. 2017 integrate magnitude-based pruning into training. Gal and Garamani 2016 show that dropout approximates Bayesian inference in Gaussian processes. Bayesian perspectives on dropout learn dropout probabilities during training. Gal al. 2017, Kingma al. 2015, Srinivas and Babu 2016. Techniques that learn per weight per unit, Srinivas and Babu, 2016, or structure dropout probabilities naturally, Molchanov al. 2017, Neklyudov al. 2017, or explicitly, Luizos al. 2017, Srinivas and Babu, 2015b, prune and sparsify networks during training as dropout probabilities for some weights reach 1. In contrast, we train networks at least once to find winning tickets. These techniques might also find winning tickets, or, by inducing sparsity, might beneficially interact with our methods.